If you ask a human to identify a messy, real-world hamburger in a photograph, they do it instantly. Ask a traditional computer to do the exact same thing, and the system breaks down. This diagram illustrates the traditional method of programming computers. To solve a problem, a human provides the computer with a set of input data and a rigid set of explicit rules. The system then applies those rules to generate a new output. To teach this traditional system what a hamburger is, you have to write explicit instructions: a top bun, a dark patty, and a bottom bun. But if the image shows an open-face burger, or a chicken patty, or is missing lettuce, the rules fail. You end up having to write thousands of contradictory, branching pathways just to account for minor real-world variations. Computers operating under this model hit a hard limit. They can only ever be as capable as a human programmer's ability to write perfect, exhaustive instructions for them. In 1959, an IBM engineer named Arthur Samuel proposed a different approach. He defined machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. This new flowchart shows exactly how that mathematical equation is inverted. Instead of providing the rules, programmers feed the machine the input data alongside a set of previous, correct outputs. The machine then figures out the rules for itself. Rather than defining a hamburger with code, we simply show the computer thousands of different pictures of hamburgers. The model analyzes the inputs and outputs and figures out for itself the visual patterns of what constitutes a burger. This diagram clarifies how this method fits into the broader science. Artificial intelligence is the overarching field trying to replicate human intelligence. Machine learning is a specific subset of tools used to achieve that goal. Deep learning is an even narrower subfield within machine learning, relying on complex neural networks. While letting the machine write its own rules solved the human bottleneck, it created a massive physical problem for the hardware available at the time. The statistical origins of these algorithms actually date back to the early 1800s, while the first models of an artificial neuron were proposed in 1943. By the early 1950s, those concepts were extended into full neural networks. But mid-century hardware was physically enormous and strictly limited in processing capacity. The technology could not live up to the lofty expectations set by early researchers. By the late 1960s, funding was slashed, researchers moved on, and the field stalled out. Research slowly picked up again in the 80s and 90s, but the real momentum hit around 2009. Arthur Samuel's theory finally became practical due to the collision of three specific modern developments. First, ubiquitous internet connectivity and advanced sensor technology created a massive explosion in the amount of raw data we collect every day. Second, modern graphics processing units provided a massive increase in raw computational power. Third, researchers and corporations made a concerted effort to assemble huge sets of labeled training data to feed into those processors. It took 50 years of slow hardware evolution and data accumulation to finally unleash the theoretical power of those early algorithms. Because our modern systems can now independently write their own rules by observing patterns in data, machine learning has become an invisible engine running behind our daily tasks. When you browse an online store or stream a movie, the system analyzes your past viewing behavior, figures out the patterns of your preferences, and provides personalized recommendations. In digital communication, machine learning continuously analyzes millions of messages to learn the structural patterns of unsolicited emails, keeping spam out of your inbox. It even operates in the physical world. Postal services use optical character recognition to instantly read handwritten letters and digits on envelopes, successfully routing mail to your home at high speeds. Financial institutions rely on these algorithms to constantly monitor transactions, instantly detecting deviations from your normal spending habits to catch credit card fraud the moment it happens. We no longer dictate exhaustive, step-by-step instructions for every task. By providing computers with the raw data of the world and the capacity to recognize patterns, we simply let them learn.